Our speaker today is our own Sergei Gukov. So Sergei is a professor of physics and mathematics here since 2005. And he got his bachelor's degree in Moscow Institute of Physics and Technology, a renowned place, in 1997. And then he got his PhD from Princeton. His advisor was Edward Witten. I actually met Sergei about that time. So I met him first at the summer school in Khargez. That's during the time when NATO still had no more serious business than funding summer schools on theoretical physics. So now they have other fish to fry. So he came here at Caltech. He was a Clay Fellow after he got his PhD and came to Caltech. After a brief stint in Santa Barbara, he returned to Caltech and been here since 2007. And he's also a visiting chair at ICTP, Mariam Mirzakhani visiting chair, and also MacArthur Professor of Theoretical Physics and Mathematics. And today he's going to tell us about machine learning and knots. And thank you for making the title so simple so I can remember.
Thank you. Thank you, Anton, for a kind introduction. Right, so what I'm going to tell you about is a rather interesting story, and it's part of what I do. I have to say that most of what I do is quite mathematical and very abstract, so I figured over the course of the years that such topics are extremely efficient at putting the audience to sleep, with one exception. So this talk is sort of exception because it will involve mathematics, but mathematics will be very visual, and it's about shapes, so that's perhaps what makes it easier to relate. And it also will involve machine learning and AI, and because computers are now everywhere and AI is revolutionizing many domains of our life and science, that's also perhaps what makes this particular topic relatable. I have to say that 5 years ago, when I started thinking about it, mostly motivated by popular media and various other revolutions that AI made in other domains, I didn't know much about machine learning. I didn't know Python, Haskell, or any other cool stuff. And I was just curious whether machine learning can help in theoretical domains. So of course, AI helps a lot with data-intensive branches of even fundamental science. It's being used quite heavily in experimental physics, where we have a lot of data. It's being used in observational cosmology, other domains. But my question was, what about something very theoretical, very mathematical, where usual logical arguments are not so long? We even talk about back-of-the-envelope calculations, or ideas are in some sense more important. Can it really be helpful in theoretical and mathematical areas? So that was the question I was trying to ask back then, and I have to admit I was very skeptical. I thought that I'll invest some time to prove to myself that, yes, I don't need to learn more about it. So, of course, I proved myself to be wrong on that part. So I'll try to tell you two stories. One which involves rather fundamental problems of completely theoretical mathematical nature that, for instance, describe braiding of anyons. So that's one connection for incarnation in theoretical physics. And on the other side of the spectrum, it will be another story about language processing in machine learning. I'll try to make this talk, since I'm fairly recent to the subject, so I remember how it feels not knowing many of the AI concepts myself, so I'll try to make it very accessible. So if you didn't have any experience with machine learning, hopefully I'll pitch it at the right level so that you feel comfortable. So it can be basically introduction through particular class of problems that we'll try to approach. But I also hope that even experts, some of you either here or on Zoom, who worked with various machine learning applications and know a lot, will also benefit in one way or another, because especially toward the end of the talk, we'll discuss various interesting architectures, so there'll be hopefully something to learn. And if anything, hopefully it will be just entertaining. So while I'm describing this kind of my motivation and how I got into this, many of you probably already read this on the first slide. So this is a conversation which happened between a human and a computer back in 1971. It was one of the early AI systems that learned how to talk, and as you can see, the conversation is pretty meaningful. So a person is asking questions whether one pyramid can support another, and the computer is answering. Actually, it's within certain framework of concepts, but it's a very meaningful conversation, not so bad at all. And this was, let's see. For some reason, not advance the slide.
Try clicking on the slide first.
Okay, I advanced it at least this way. I'll try to. Okay, now it works. Yeah, thank you so much. So this is the creator of that early AI system. This AI system has a very intriguing name. I'll let you figure out what this stands for or how it got here. And name of this person is Terry Winograd. So he is one of the founding fathers of the subject of natural language processing and natural language understanding. So he's known for various books that he's written, and this Shurlu AI system was one of his early babies devised back at the time at MIT. So since then, he moved to Stanford and had many other successes, in particular many good students. So one of his students, shown here on the slide, you know him very well. So he is probably best known for so-called PageRank, and also became a co-founder of a company that in 2015 famously managed to beat the best Go player in the world. And throughout the talk, I'll give you actually many timelines. So if you carefully follow various dates that I'm going to mention, you can probably see why I got interested in the subject 5 years ago, and also why now is an exciting time to even think about this bridge between machine learning and theoretical and mathematical disciplines. So think about this as a sort of version of the question that cosmologists ask a lot, why now? So I'll try to, through these dates, explain why now is a good time. Anyway, so going back to this, Google had AlphaGo, of course, in 2015, but let's wait till we get there. So we'll start slowly. And coming back to the question whether it can help in fundamental sciences and mathematical and theoretical disciplines, well, I want to quote our own Richard Feynman, who actually compared our research process to playing the game of chess, where we don't actually know the rules of the game, but what we're allowed is to see how pieces move on the board, and from this we are supposed to figure out what the rules are. So this process is actually very accurate and perfect fit for today's talk, because not only it describes how we do research in theoretical physics and mathematics, but also how machines learn. So they observe lots and lots of rounds of games of different types, and from mistakes, from wins and failures, they learn. And that's actually exactly how we do science in the first place. So it doesn't, therefore, sound too distant. So speaking of the game of chess, this is one of the chess grandmasters, Garry Kasparov. In fact, I was lucky enough to meet him. So when I was in middle school, I went to chess school that he organized. That was in late 80s. And one of the things that surprised me is that even back then, when computers, it was 80s, and computers were still not quite popular among middle school or high school kids in classroom, he actually had several classrooms where not only we played chess against each other, our partners, but where we could try different programs playing chess with the computer. So here you can see Gary in early 90s, and I can vouch that, yes, that's pretty much how it looked, and it's a typical photo from our classroom. It surprised me back then that even though we were supposed to learn various strategies and tactics in chessboards. He was very open to computers, so maybe that was one of the reasons why he agreed to play against Deep Blue of IBM a couple of years later. So this is a photo from 1996, the first match, where compared to the previous slide, you can see that he's not smiling anymore. That looks much, much more serious. So he won this one, but a year later he lost to Deep Blue in this 1997 rematch, and since then computers basically took off, and I told you already about AlphaGo and other things. So it's another anecdotal kind of story that IBM devised Deep Blue in part to kind of popularize computers and to connect it to general public and do something a little bit more relatable. And some people who were involved in building Deep Blue actually worked on speech processing. So there was an entire group in IBM, and one of the people who is actually responsible for the name Deep Blue, originally it was called something else, was Peter Brown. So he worked at this group on speech processing at IBM until 1993, got involved into this project, and then in 1993, Jim Simons lured him into Renaissance Technologies, where he remains up to present day, and in fact remains a CEO of Renaissance Technologies and probably one of the longest employees in the company. But anyway, coming back to this story, you might be wondering what speech processing group at IBM had to do with the game of chess. And that's a very good question, so that's a kind of question to which I'll try to give an answer today. So moving on, and thinking a little bit about this Feynman's quote and how we learn and how machines learn. Well, again, we see many chessboards or many boards or whatever game we're playing. And from experiences, we are trying to learn either the rules or strategies, whatever the goal is. And of course, there is a huge difference between trained and untrained chess master, and there is a huge difference between trained and untrained neural net. After we see many, many combinations on boards, it becomes an automated process. So this is sort of 10,000-hour rule popularized by Malcolm Gladwell, who says that if you invest a sufficient amount of time in a certain subject, you become an expert. And in the case of chess, for instance, if you look at this board, you immediately see a big picture. You don't just see random pieces. You see how we got there, what's the position of power, is one side about to lose or win. You immediately see the whole rich story behind it. And this is precisely how AI systems learn. They see many, many repetitions of the same thing. They get rewarded and punished. And in exactly the same way, they become familiar with important details. They can quickly filter what's important, what's not important. So that's the rough picture. So today I'll invite you to play a very simple game. Again, I chose particular kind of game because it's easy to visualize, easy to explain, which has to do with grading or also knot theory. So basically, I invite you to play a game where by looking at the picture of this looped string called a knot, we have to tell whether it's knotted or unknotted. So in other words, whether by moving this pieces of the strand without cutting them, we can reduce the diagram to a simple circle like this. So that's basically the question. So it's a decision problem. It's a yes or no question. And it looks very simple, so that's the game that we'll start playing, and there are many variants I'll mention to you in a bit. But maybe first, can I see a show of hands who thinks that this diagram is non-trivially knotted? How about who thinks it's unknotted? Okay, some opinions are split, very good. This is a slightly more complicated, so it was knotted. So it was knotted, you guys were right, or at least half of you. And then this is a slightly more complicated one. This has 3 crossings. Who thinks this is knotted? Who thinks it's unknotted? Okay, you guys are right, so very good. At least those of you saying it's unknotted, it is. But you see the point. It gets progressively harder and more complicated. So This game looks pretty silly. It's almost like child's play, and I didn't have to go through very complicated mathematical definitions to introduce the game. That's part of the reason for choosing this kind of visual and simple topic. But it's actually very deep. It has to do with very deep mathematics, and in particular, I'll mention here just a couple of applications. One of the major unsolved problems in low-dimensional topology is a smooth Poincare conjecture. So topological version of Poincare conjecture is well understood and settled, and more delicate versions involve various conditions that one can impose on relations. So the Poincare conjecture is a question whether a manifold that looks like an n-dimensional sphere is actually an n-dimensional sphere. And smooth requires that we work under certain conditions where we can take as many derivatives as we want. So this conjecture is settled in a positive form in low dimensions. It's settled in negative form, so we know it fails for sufficiently high dimensional spheres. But dimension 4 remains very elusive and escapes all methods and approaches that topologists developed over recent years. And the question in this field boils down to questions which are exactly analogous or close cousins of this knottedness problem that I mentioned on the previous slide. Part of the reason is that when we think about this knotted and braided structure in a three-dimensional space, we can think of this three-dimensional space as a boundary of something four-dimensional. And that's the basic reason why such knotted diagrams actually represent something or get us foot in the door of a four-dimensional topology, that they have something to do with dimension 4. So diagrams like this, maybe sometimes called Kirby diagrams or representing other things, actually do have direct connection to this deep problems in low-dimensional topology, but they're extremely hard to handle. So it's hard to tell if this diagram has certain properties or if it's knotted, unknotted. And questions like this actually are precisely what stands in the way of resolving this old-standing problem, the smooth Poincare conjecture. So it's just a question of, can we manipulate this diagram and make it decide whether it's knotted or unknotted? I'll give you more concrete examples later. This one comes from a paper of Mike Friedman and collaborators from about 10 years ago, where being exhausted in trying all kinds of theoretical methods that mathematicians and theoretical physicists tried, they decided to work with computers. So this title of the paper is Man and Machine, thinking about this long, important problem. Here they used classical computers. In a sense, there is no machine learning, no AI, but the need for computers was precisely to help, to aid deciding problems like what we're facing here. So there are a couple of other related problems. For instance, there is a so-called relative version of Poincare conjecture. It's a statement about ball rather than sphere. Namely, the question is whether a manifold which is homeomorphic to four-dimensional ball is also diffeomorphic. If this conjecture is true, it implies the actual smooth Poincare conjecture. So many of these interesting statements are closely related. And another cousin here is, by looking at a diagram of a knot, you're supposed to tell something similar to this game of unnottedness that I introduced, namely whether it has a certain property called ribbon. So that's additional operation that one can introduce that basically leads to a certain decision problem, a property very much like knotted, unknotted. Again, they're all close cousins. It doesn't really matter, not too important. What's important is that the problem we're playing with today is really a part of a network of questions which are important and deep in mathematics. Now, what's stopping us from answering these questions is that typical counterexamples to these conjectures, such as Poincare conjecture on the previous slide, or this one called slice ribbon conjecture, involve diagrams which have 30, 40 crossings, and typically actually hundreds of crossings. Whereas theoretical methods that people developed, and there are many invariants and other techniques that were developed over the years, can be easily computed only for rather simple knotted diagrams, which usually are limited by 10 or 20 crossings. So for instance, with some of my students and here in the math department, We work on quantum invariance, and most famous example is probably the Jones polynomial. But these invariants are really hard to compute, also in the terminology of complexity theory. We'll come back to it in a later part of the talk. And there are several challenges here. First is that even the basic pieces of such knotted diagrams grow very fast with number of crossings. So, for example, there are only 165 basic knots which have 10 crossings. But if you move to 16, you suddenly get over 1 million. And then again, it explodes. And we're talking just about basic pieces. So that's one part. And also computation of these analytical or other methods that we have in topology also becomes progressively harder. For example, again, Jones polynomial and other invariants are computationally hard also in a technical sense. So for this reason, the wall or limit here is really somewhere around 20 crossings. No kidding. And there is no hope, because even if we believe in Moore's law and technology improves and we get better computers next year, it improves by a factor of 2. But this goes faster than exponential. So basically it means that if we can do this year 20 crossings, next year we'll do 21 crossings. So this is the log scale. And what we need, interesting examples that we need lie way beyond. So until so far, we really had no way to tackle examples like this. So they were basically approached one by experts who can, on a paper, handle these manipulations and see something. And that's extremely difficult. There are basically a couple of experts in the world who could do it. And that's of course, not a great state of affairs. So we want to approach this no man's land and go even further, where we can easily handle, say, hundreds of crossings of such diagrams to answer these fundamental questions and fundamental puzzles. So that's the motivation. By the way, if there are any questions, feel free to interrupt me at any point or raise hand. Now, back to machine learning. It works really well when you have many configurations. One configuration space is huge, but the space of actions is very small. So that's what works well for games like Go. Chess in that sense is maybe not ideal, because there are many different moves you can imagine. But this problem that I mentioned is a perfect game, because there are many knotted diagrams that can be related by only 3 basic moves. So in this game, there are only 3 moves we have to input for a machine. And every diagram which can be transformed into another by this equivalence relation can be transformed by one of these 3 moves, called Reidemeister moves. So what we're talking is about huge space of possibilities, but only 3 basic moves in the game. So it sounds perfect. It sounds ideal for the machine. So therefore, the question becomes, okay, how do we play this game? And of course, in machine learning, one of the most important questions in practical sense when you approach a problem is data representation, how we want to encode data. So one way to encode a knot, such a knotted diagram, is just to present computer with a picture. That's one obvious way. It's actually not so bad, but it's also not very good, because there is a lot of empty space in between of where the crossings happen. And if one makes a mistake in a single pixel, that's probably very bad, especially since we're trying to disentangle this braiding or topological properties. So it doesn't sound too good. But then there is another way, which is much better. Encode the data of these knots in terms of so-called braids, which are shown on the left part of the slide. And given every such braiding on the left, one can produce a knot by simply closing the strands in a circular fashion. So this way we reduce question about this knots to a question about braids. So this is the same as braiding of anyons that I mentioned earlier. And here again, there are only few basic rules. This is very simple structure in the sense that I can tell you very quickly what it is. These braids are made of a very simple alphabet of sigmas and their inverses, which correspond to braidings doing one type of crossing or another type of crossing in a certain ith position. So that's, if we want to encode the braid, then we have to basically give collection of such crossings represented by the sigmas and sigma inverses. Very much like Reidemeister moves, equivalences are encoded in 3 basic moves, in this case called braid relations. Basically, if crossings happen far from each other, they completely commute. It doesn't matter in which order we want to present them. If they happen next to each other, there is a non-trivial relation, which is the only non-trivial relation in this structure called Artin braid. So therefore, if you want to present a knot, instead of just taking a photo with a bunch of pixels, much better way, for instance, or there are many ways, but one of them is to do it through this language where as letters you use sigmas in various positions. And again, equivalences are contained in these basic relations. So notice that I already start using the language letters and words, and indeed mathematicians, when they talk about the structure, they call elements in this, or sequences of these sigmas, words in a braid group. So that already resonates with the use of language as in natural language processing and natural language understanding. So we decided with my colleagues, Jim Halverson, Fabian Ruel, and Piotr Sukowski, to try to apply these ideas from natural language processing and natural language understanding to the words in a braid group. Because phrased in that way, all we have to decide is whether a given word is trivial or not. So that's for instance, the simple unknotting game that I introduced early on. And now, once it's phrased in terms of language, it sounds that this may be a good fit. And again, I emphasize that one of the lessons I learned from AI is that probably a lot of time usually should be spent on thinking how to approach a given problem, namely finding the right way of encoding the data presentation, and choosing the right algorithm and choosing the right architecture. So these are questions that we'll talk about next in trying to solve each given problem. So Piotr is a familiar face on this campus. He was actually postdoc at Caltech, and then visited us many times as a visiting associate. So that's actually how this work was done. About a year or a couple of years ago, when he was here before the pandemic, we were working together, and that's another reason for me to speak about this work here. So the goal then is to teach the machine how to decide whether this thing here is knotted or unknotted. So let's think about this data representation and try to decide what is the best algorithm to approach this. Again, we shouldn't rush into just doing the coding. We should think about what are the available options are there. And going back to Terry Winograd, whom you saw on the first slides, so one of the things that he invented, even before AI techniques became very powerful, he suggested that for the future, it would be good to have really delicate, complicated cases of sentences which require machine to really understand the meaning of the sentence really well in order to either process it or parse it or translate it into a different language. So these sentences are now called Winograd schemas, and here are a couple of examples. So one of them is the trophy would not fit in the brown suitcase because it was too big. Or you can replace the word big with small, and then, of course, the meaning will change a little bit. So if I ask you what was too big, then we immediately say, well, the trophy was too big, that's why it didn't fit. So we quickly have to assign or make connection between the words and the sentence in order to properly process the meaning. And this is important because if we translate this sentence in a different language, the words trophy and suitcase may have different gender. And if in this translation we start making up information, that's of course not good. So that's part of the reason. So these Winograd schemas were quite challenging for various early AI systems for obvious reasons. And going back to 90s, where I left our discussion of language processing, back at the time, the processing was based more on probabilities. In other words, machines, that's actually what Peter Brown and his team at IBM were doing. So their techniques were probabilistic. So this is goes under the name of statistical machine translation, where the way we actually process information or when we talk to each other, it's interesting that even how it works on biological or psychological level, we're actually guessing what our partner or friend is going to say next, and then when the other person speaks, we're actually basically confirming in our head whether this is what we were expecting. So this is very much like such machine algorithms work. So they consist of two parts, typically. One is called language model, the other is translation model. So language model generates text, and translation model helps this generating component to confirm with certain probabilities or deny whether that the next move is the correct one. So again, in statistical translation, machine translation, which was dominating over 90s and early 2000s, this is basically how it worked based on probabilities. So machines had to learn these probabilities, and this arrow shows the progress over various years, as it has slower or smaller derivative. But and this scale is so-called blue scale, which is bilingual evaluation understudy. This is one of the scales typically used to evaluate how machines do on translating from one language to another. 20 is pretty good, 30 is excellent, and 40 is outstanding. So it's really stellar. So as you can see, they were doing okay, and actually Google Translate in early days used, or in early 2000s, used statistical machine translation like everybody else. But then something happens around 2014, 2015. In 2014, neural machine translation started growing very fast, and by 2016, Google Translate already changed its system from statistical to neural. So that's where AI comes to the scene. And I'll try to give you a hint why this happened, what kind of development was involved. And again, if we keep track of the timeline, see we're again approaching this mark of roughly 2015. So some of the early, this is actually quite good, successful architecture that was used for neural machine translation. It's called sequence to sequence, because if you're given a sentence in one language and your job is to translate it into another language, you can actually mimic what I described in words, where when we listen to our conversation partner, we're trying to guess and correct our expectations as we go. So it's very sequential. So we go through each word in a sequence and translate that word. And that's exactly what this architecture is doing. It consists again of two parts, which are analogous to the two parts in statistical machine translation that I mentioned a moment ago. So instead of language model and translation model, they're called encoder and decoder. And here is a realization of this architecture in fairly basic neural nets or layers called recurrent neural nets, RNNs. So each of these nodes corresponds to RNN. It's doing encoding, and then meaning vector is passed to the second component, and then it does decoding in a similar sequential layer. So those of you who speak German can quickly detect that this is not perfect. So this is an actual example, for instance. The input sentence is, you asked us to call you back after last Friday, and what comes out is, wir hoffen jedoch, dass sie bei ihrer Reiseplanung weiterhilft. So there is no Friday in this translation. What it says is that, however, we hope that this will help you with your travel plans. So that's roughly meaning of this sentence. So this is an honest mistake that the machine made based on seeing lots of other chessboards, lots of other examples, now in the case of translation. And it did make some connection. Connection is not horrible, but it's not good. And the reason this thing happens, and there are many other examples, that's, for example, now it's harder to see them because, again, machine translation gets better and better, but say 5 years ago, this was fairly common. If you just feed sequence, and there are some sequence-to-sequence connections, that's how they work. And there are several reasons for this. So without going to too technical details, it's actually hard for a machine, especially in the sequence to keep the meaning over a broad range of words or letters over a longer part of the text. So long-range dependence has become hard, in part because we're doing it in sequence. And once you made a step, it's actually hard to go back. So there are so-called long short-term memory units, which were introduced in the late 90s. They help with this problem, but not by much. So another thing is that in machine learning, many neural nets are based on various versions of gradient descent or ascent. And once you have something long, something big and complicated, you're composing activation functions. And these are like sigmoids or ReLUs or other things. And they lead to vanishing gradients. So once you have many layers, they lead effectively to small gradients, and that becomes hard for a machine. So then there are several other things that make it difficult, and the question is, how do we go beyond so we can actually make qualitative progress beyond these examples? Well, this part of progress came from computer vision, also in 2014, and then by 2015 made it to machine translation. It's called attention mechanism. So this is an additional component, an additional type of layer in neural net, which keeps track of correlation between a sentence in itself or a sentence in one language and sentence in another language. So this is basically encoding the context. And that helps a lot with all of these problems that I mentioned a moment ago. So its key component is so-called relevance or attention metrics, which is some dot product of encoder and decoder information. And it's usually represented either like this in the form of heat map, which tells us which word in one language may be most relevant to the word in another language, or sometimes in a form of self-attention, when you, on both scales, you can imagine the same sentence, but then it basically tries to make connections, such as in this sentence here, the animal didn't cross the street because it was too tired. So if I ask you who was tired and what does word heat refer to, then you see much stronger neural net or weight here connecting it to animal. Another version of the sentence would be the animal didn't cross the street because it was too wide. And in that case, connection would be between word eat and a street. It's the street which was too wide. So these are typical examples, and such attention layers are extremely good at keeping this information. So here is the next step, the progress. It's a particular architecture of neural net, which is says that let's throw away everything and keep this attention layer. So the architecture is shown here. It has this attention layer repeated many, many times, and I think the title of the paper speaks for itself. So this became a very popular and much more efficient way of doing translation than, for example, seek-to-seek architecture that I showed you a moment ago. In particular, it did really well with these vinaigrette schemas. So, for example, the cow ate the hay because it was delicious. So again, if we need to translate it to languages like French and German, we really have to understand who was delicious, the cow or the hay, because gender may be different. And you can see that transformer, this architecture that I showed you is called transformer, based on many attention layers. Performs pretty well, so it does, so this was Google Translate back at the time in 2017, and the second column is this transformer, which does pretty well, so it can go through vinaigrette schemas quite effectively. It still makes mistakes. So it's very multi-purpose type of architecture. It's actually, this transformer is good with many, many different tasks. In particular, I mentioned to you that when we do the translation, there are two components. One is generative. It's basically generating text. And you can try this component, for example, by feeding it just one word. So what Lukasz Kaiser illustrated in his nice lectures, which I encourage you to listen to in 2017, is that if you feed the transformer, the word transformer, and ask to generate Wikipedia article, then it produces a very believable Wikipedia article. So sometimes transformer becomes a book, sometimes it becomes a rock band, as in this example. And it's actually quite nice. I mean, it has all kinds of details and turns and twists. It, for example, knows that bands dissolve at some point, and there is some drama associated to it. So it's actually almost like realistic Wikipedia article, but of course this band doesn't exist. Anyway, so we're not done yet. So I told you about the 2017 revolution of the transformer. That was great progress. Then there is this. Huh? Yeah, I was going to point. Yes, so it's a famous by now paper by Kitaev, but Nikita Kitaev, indeed. So this is when we were doing this, we were trying with my colleagues. We were trying many different architectures. Like I said, it's important to choose the right way of encoding the data, the right architecture, and find the right algorithm. So in particular, we went through many of these, and I'm reviewing for you some of the prominent examples. And this was basically state of the art back in 2020. So it's called Reformer, as the title of the paper says. It's efficient transformer, and it optimizes already fantastic machine. So in the world of neural translation, the transformer was already like a Ferrari, so this does even better, so I don't know what to compare it to. And in particular, what it does is in this attention matrix or heat map that I showed you before, it basically tries to pick out the most important pieces. So after transformer appeared, there were many developments. For example, this one actually here illustrates so-called variational attention mechanism. And Reformer does something similar, basically by trying to do hashing, this sort of tagging to most important correlations in that matrix, so that we don't have to carry a lot of weight, especially if we have a long chunk of text, but it becomes very, very efficient and faster, reducing the complexity from quadratic size of the matrix to something which is linear times the log. So that's great. Anyway, so I walked you through some of the developments. Hopefully you see why now, and at least from the AI perspective. So let's see what happens when we apply this to our braid words. So now we take this different architectures and try to translate or basically apply to our decision problem whether a knotted diagram is trivial or non-trivial. All we have to show is whether in this funny language it's a trivial word or non-trivial word. And here is what happened. So there were two surprises that we didn't expect before we started doing this work. One surprise is that, first of all, performance improved with braid length. So if you make more complicated knotted diagram, like I showed you a couple of examples in the beginning of the talk, the performance actually improves. So different colors represent different number of crossings, roughly speaking. And you see that the more crossings, the better accuracy you get. It's always close to 99%, but it actually does better on more complicated knotted diagrams. I don't think we understand fully why this happens. We try to give several reasons in the paper, and we explore this a little bit, but not fully. And one reason perhaps is that just like playing stronger opponent teaches you how to be a better chess player, in the same way, trying more complicated knotted diagrams with hundreds of crossings actually teaches neural net how to be a better chess player in this world and doing translation. So this was one surprise.
So you have a very complicated knot. Okay. Couldn't you learn the same thing from a large number of simpler knots? And does it learn on each example knot, or is it just taking one big knot and learning on that?
No, it's important that it learns on many different kinds of knots. So that's a very good question. So you show machine thousands, in fact, in practice, millions of different knots. You generate them, so there are some knots, some unknots, and it should learn how to differentiate them very accurately. And then you save some small fraction of that million for testing. So that's this data of testing. So there are many different knots and unknots, and it's important that they generate it in different ways, so there are no biases, It's a separate analysis of how the statistics is done. And then, yeah, you basically ask to test. And after we did the learning part, this is the championship, basically, for Grandmaster. We did practice at home, so then now we come and ask it to differentiate these test examples, for instance. Does that make sense?
Yeah, although it makes it very surprising that it would be better at the complicated knot after the learning.
But there are no nodes that it can use to learn, right?
That's perhaps.
There are a lot of easy cases, right? There are some hard cases. And those are the ones that can't.
Yeah, actually, that's another good question. So this goes into the details of braiding and knottedness. So even before computers got in a game, so human, noticed that they couldn't penetrate beyond 20-something crossings. But they noticed that around 20 crossings, there are some very complicated, for some reason, knotted-looking diagrams, which are actually hard unknots. So that you have to increase number of crossings to something like 30 or 40 before you can reduce it back. So such classes in mathematics and pure math are completely not understood. In fact, many topologists that probably don't even know about them. And this, of course, happens here a lot. So the landscape of knots is very non-homogeneous for some reason. So your question is basically about that, and that's another thing you can now try to probe with the machine. So indeed, it learns very different strategies, which is, again, if it can learn how to play game of chess, is not too surprising, because in game of chess, there are so many different combinations and openings, and we have to learn all of them to play it really well, with a success rate of 99%. So yeah, there are some easy ones, and there are some really hard ones. And it has to be an expert in everything. So that's why it's important to choose the right algorithm, the right architecture to do it well. So that was one surprise, and indeed I completely agree that it is surprising, at least somewhat. But another surprise was that I walked you through 5 different architectures of this machine translation techniques, and they are not needed. Even the most basic neural net, called a feed-forward neural network, performs just as well. Maybe a little worse than what I showed you here, this fancy reformer, but it does pretty well too. So what we learn here is that this unknotting problem is actually easy for a machine. So what does it mean? Well, how about we look into complexity of this problem, and actually it has been looked at. So back in 2008, this paper proves that the problem that we're trying to approach is a problem of NP type. It's in a complexity class NP, which means that non-deterministic polynomial time. So problems in this class are very much like Sudoku puzzles. They may be hard to solve. They may not have polynomial type time algorithms, but you can verify correct solution in polynomial time. So then there is, in the zoo of complexity classes, there is another complexity class called CoNP, which is analog where you can verify negative answers in polynomial time. And of course, we don't know how this Venn diagram or zoo of complexity classes is arranged, because part of it is, for instance, this clay problem of whether P equals NP. I think most experts believe that it's not. In particular, we don't know if NP and CoNP also coincide. Probably not, because, well, if they don't, then also NP does not equal P, so the clay problem also has a negative answer. So here I'm drawing this Venn diagram with several assumptions, which are, I guess, most plausible to most people. So in particular, here in this paper, Greg Kuperberg showed that assuming generalized Riemann hypothesis, this problem the game we're trying to play is also in a complexity class CoNP. So it means that negative solutions can be verified in polynomial time. And it's actually interesting because many problems that happen to be both in NP and CoNP over time were found to be polynomial type problems. So in other words, they actually belong to P. So they might be a polynomial type algorithm. And you can interpret what I showed you before, that the fact that this is easy problem for computer, that maybe actually there is a polynomial time. And we don't know it as human, but maybe that's what machines learn very quickly, that there is a simply algorithm to play this game. Well, I have to point out that some problems that happen to be at the intersection of NP and CoNP are actually hard. For example, deciding whether an integer is a product of two primes has this property and is believed to be a hard problem. So maybe we shouldn't celebrate too early. And let's look a little bit more closely. So a few years after, there was another paper on the subject which proved the same result, relaxing this generalized Riemann hypothesis assumption. So it also showed that this problem that we're discussing is in both NP and coNP. And here there is this amusing corollary which says that if it's NP complete, that NP equals coNP. Like I say, we don't know if these two classes coincide. Generally, they are believed not to be the same. And if that's the case, then again, Clay problem also has a negative answer, namely that P does not equal NP. So the title of this paper speaks loud and clear. Like I said, we shouldn't celebrate too early, declaring that this seems like an easy problem, because if you impose any constraint, for example, that machine has to learn whether it's not or are not with imposing upper limit, for example, of number of moves, it immediately becomes NP hard. So therefore, it's actually probably at the upper range of complexity in this NP and coNP, and may not be at all in polynomial time. So finally, I want to mention that I already mentioned earlier that traditional approaches in mathematics to these sort of problems involve various invariants, which is another component in my life, and again, with students, we devise new invariants and so on. And I already mentioned that they're extremely hard to compute. So this is a typical version of such invariant, or in fact, a question from which you can produce many different invariants. And here it's being shown that it's in a fairly esoteric complexity class, or simultaneously sharp P-complete. This is a class which is pretty hard, and it's instead of yes or no type questions, it's asking about how many solutions you have. For example, many graph problems about perfect matchings or colorings turn out to be in this complexity class. So this development from the complexity theory point of view shows that the problem we're trying to attack may be simple, we don't know, but it also may be very complicated. So there is no clear message here yet. So in the remaining couple of minutes, I want to show you a different type of AI approach. So previously we were trying to play this game so that machine can predict, basically focus on a decision problem, yes or no. And it does it pretty well, so the graphs with 99% accuracy were showing that. But you can also ask machine to actually play the game of chess, namely to perform the moves, to show us not only yes or no, but how to reduce it to trivial diagram or answer this problem and actually produce various moves. So there are, again, different algorithms to do it. So one simple is just try to do random things. And again, if computer is fast enough, for example, Deep Blue was able to perform 200 million operations or chessboards per second. So then it can probably find some solution just by trying things at random. So this is the random walker. It's RW, and it's a green set of dots. This is a diagram of accuracy versus complexity, how many crossings you have. And as you can see, it quickly goes down. So that's not very good. So then there are various other algorithms. For example, there is this A3C. This is asynchronous advantage actor-critic algorithm. It does pretty well, but it also goes down. And then there is a blue one, which is an algorithm called trust region policy optimization, which does really well. So you can see that just as before, for whatever reason, this likes to play this game. In other words, you give it more complicated opponent, and it performs pretty well. So accuracy goes up as complexity or number of crossings also increases. So what is this algorithm? Again, in machine learning, most basic architectures and layers are based on various versions of gradient descent or gradient ascent, as this left picture illustrates. We want to go up, so we basically try to find some function, and according to this function, we try to perform this gradient ascent or descent. So the danger of this is that if landscape of configurations or possibilities is not very smooth or even, you may perform a step in the right direction, but then if step is too big, you may fall and never recover. So that's pretty bad. So instead, this trust region policy optimization does the following. It draws a region around a given state and then optimizes within that region. So that way you guarantee to never perform such a dangerous fall of the cliff. And you improve gradually and steadily, but it's a constant improvement. So that's this TRPO algorithm. That's the basic idea. And here is another graph of how many actions does this algorithm perform on various knots and braids of different number of crossings. You can see same message that as braid length increases, so if you have more and more crossings, then actually its number of operations that it performs to reduce it to trivial braid, in case if it's possible, stays more or less constant. So, or it grows here in a little bit, you can see, but that's of course expected because if you have more sites, then of course you should have more operations, but they're exactly the same order of magnitude, roughly speaking, whereas these other two guys go way up. So the message for me from all of this was that it's a lot of fun, and you can connect completely different problems and completely different fields by digging far enough. For instance, trying to understand how machines can translate text from one language to another language or parse text happen to be perfectly suited for questions such as these knotted problems, which have deep connections to topology, Poincare conjecture, and various other conjectures that we simply could not access until recently by any traditional means. So this was really, really hard. And I don't want to advertise this, that machines, of course, can do this much better than us. It's important, and hopefully this talk was also illustrating the point that we are, as humans, are needed to do a lot of thinking. So I actually learned by working in this field that compared to, say, research in theoretical physics, dynamics here of a project is a bit different in the sense that you spend a fair part of the time, maybe more than 50 or even 70%, thinking about how to approach the problem in the right way. Namely, all these questions about choosing the right way of encoding the data representation, choosing the right algorithm, and then choosing the right architecture are essential to doing it in the right way and improving the performance in the end. So in that sense, computers won't replace us, but it's a lot of fun to cross these bridges between different domains. So thank you for your attention.
Questions from the in-person audience?
Yeah. So a couple of times in your talk, you used the phrase classical computer to, allude to just sort of, I guess, call it algorithmic approaches as opposed to machine learning. But, this being the Caltech physics department, I guess I have to ask, if you move into quantum regime, is that a potential way of solving problems of this sort? Is there some advantage? Assuming that somebody could build a quantum computer, of course.
That's a very good question. That's actually a very non-trivial question. I think it's also part of cutting edge research. So this paper actually talks about it and shows that if you have quantum computer, you're not going to improve on this parsimoniously short-bit complete, unfortunately. But you may improve, of course, computations of some things which involve grading. So after all, that's one of the ways of making quantum computer, and perhaps not too surprisingly, but it still requires certain steps to show that they will improve computational power of things like John's polynomial, for example. So it's again, sits kind of at that borderline. So definitely quantum computers will help. But how much, it's actually not clear. So very much like as in this last part of the talk devoted to complexity, it sits kind of in the middle where it becomes interesting. So it's hard to make bets or opinions. It's some evidence is for, some is against. So I would say same thing. So quantum computers will definitely help, but I don't know if any of the problems that I mentioned will be solved in this way. Certainly it will be improved, that's for sure.
See?
There are problems that might be hard for neural networks. For example, the parity problem. decide whether the number of objects is even or odd. I wonder whether it's actually true, and if it is true, can we embed this problem into the unknown problem?
That's a good question. I'm not sure I know exactly the problem you're referring to, but maybe we can chat after. That would be good if there are connections. Yeah. I don't know. That's a very good question.
Do you know if there's been work on trying to learn other invariants using kind of machine learning?
Yes, there has. So I probably should have said in the very beginning when I was giving this introductory remarks that 5 years ago when we started doing this, this was completely uncharted territory, more or less. Trying to bridge this very abstract mathematical questions with machine learning, and many colleagues would be reasonably skeptical. So over the past 5 years, a lot has happened, and now I feel comfortable giving this talk. I wouldn't be comfortable giving this talk 5 years ago, because again, even perception in mathematical or physical community was very, very different. So indeed, this is now a fast-growing, exploding field, and some groups are specifically looking for invariance in this way. In other words, that's a very close cousin of the problem we were discussing, where, for instance, if a knot happens to be a trivial knot, or a machine can disentangle it, one can ask why, and try to extract from neural net some information that we as human didn't notice, that there might be some new invariants or some new clues why this happens. So this way, again, it's an ongoing process, but there are quite a few groups which are exploring new invariants in this way. It's a close cousin of this question.
So, can you give some idea about how this machine learning approach compares to, let's say, any other classical algorithm, non-machine learning algorithm?
Right, so perhaps most relevant in the context of this talk is the slide I showed earlier on Man and Machine, a famous paper by Mike Friedman and collaborators. So they try to use what indeed I call classical computer in a sense. It's a completely algorithmic, traditional approach of computing invariance. And what happened here is that they had this two examples in the paper. The whole paper and the whole project, which took quite a lot of time, was devoted essentially to two examples. One had 78 crossings, the other had 86 crossings. And they, in the paper, it's fun to read, they describe how many hours of supercomputers they spent trying to crack these two examples plus one more, which they managed to solve. It had a very small number of crossings, maybe 20 or something. And this they didn't, so they didn't know. So they tried to compute various invariants, run out of memory and speed, and some of the invariants they were able to compute, some were not, so it was an open question. Luckily or unluckily, basically within a week after the paper appeared, so somebody managed to actually solve this problem and completely resolve it. So these are not potential counterexamples to SPC4 anymore. But this still is, so this was also published 10 years ago, even though it has a smaller number of crossings, this is not known. So this gives an idea of dynamics in such classical algorithmical calculations. It's pretty hard, and basically you manage, you work on one example for many, many months with many resources of supercomputers. Whereas AI simply outperforms any of this, I would say. So again, if we think about how to approach the problem in the right way, that's where most time goes. You can, with 100% probability, say that certain knot is knotted or unknotted by just presenting the actual moves. And this can now become a mathematical theorem, so there is nothing probabilistic about it anymore. And machine can handle it on a simple laptop. So I have here codes that can run maybe sometimes for hours, but we're talking about hours, not many months. And then we're doing many knots in these hours rather than just one. So it's that's roughly a measure of how performance compares.
What are some of the practical applications of being able to solve a knot? Any
Practical.
practical applications?
Practical applications. Not that I know of immediately, so it's, for me, I come obviously on a very kind of mathematical side of the spectrum, perhaps, especially for most of colloquium speakers here. So my interest is purely theoretical, I would say. These problems are somewhat related to various problems in cryptography, so various variations and close cousins of them may have applications of that nature. That's the best I know.
I wonder if you considered a next step in what you've done as looking at what the machine or neural net has understood in terms of like how to solve the problem, to be able to extract those representations with a better theoretical framework. Is that something that you would consider?
I think that's a very good question. That's something that should be considered. We didn't, because we did a little bit and then moved on to other things. So now we're trying to approach, we're still working on related problems, mostly trying to crack this example, for instance, and its various close cousins. So that involves not exactly the problem I described today, but this other variant. But what you're suggesting or asking is an extremely good question. It definitely should be, and it's closely related to the other question about learning invariants. And machine, of course, learns something. So the question is, what exactly is that something? It's most likely going to be super valuable information. We didn't invest time and effort, but only because our time is limited. I think that would be a great project to dig deeper into.